All right. Welcome to this workshop. This is our, not the 10th workshop, I think the 9th workshop. So week 10 workshop talking about geometric series, sequences and series and interest. So the little technical problem or thing I was doing, the writing tablet I normally use to be able to write math live in front of you by hand is not working right now. So I was the last hour, I was like typing out all of the answers in advance and then trying to create little blocks to hide it and then show the parts one by one. I did quite finish all of that. So well, we'll see how this goes. This is going to be pretty awkward. Sometimes it works if it's just numbers, but the partial sum stuff, these big fractions, it's pretty awkward to just type. Well, we'll see how it goes. We'll see how it goes. Some of the later questions from the interest stuff, I might just skip or push back to another workshop, because it's going to be really hard to talk about them without being able to actually write. Anyways, we'll get started. So I have a whole bunch of exercises from 12.3, as you can see, and then we have a few from this different textbook, which is a textbook I've used in the past. This textbook costs money. Costs a lot of money, which is why I chose to stop using it. Our main textbook is pretty good, again, except it's not really in a econ or accounting textbook specifically. So some of these areas, it's not 100% perfect, but it's pretty good. And it's also, it does a bunch of other parts of just the general math stuff better than this other book. Anyways, we'll get to all of this. So first questions will just be about geometric sequences and series. Most of these won't be too hard, just applying the formulas directly. And then I have one that will be a bit harder and a bit longer. So first, let's identify, are these things geometric? Are they arithmetic? Are they nothing? Are they some other sort of pattern? So what's going on for each of these three? So please try that right now. Take, I don't know, a minute or so to look at these and then tell me what you think they are. All right, so the first one that we see on the left here, what kind of sequence or series does it look like we have?
Geometric.
Geometric, and why are you saying that? What do you notice?
Each number multiplied by 1/2.
Okay, 1/2, that's the common ratio that we can see there. So our value is equal to 1/2. That's kind of small. Try that again, r equals 1/2. Okay. All right, so if we see that, if we do have that common ratio, that's it. It's a geometric sequence. Our second one, what do we have?
Arithmetic.
And what are you seeing there?
Because the common difference is +5.
Okay, so our D value is 5. We can see that. So +5, +5, +5 with each of those. What about the third one?
None of them.
None of them. Okay. So we can look with the first two terms, or sorry, with the first three terms, we can see common difference of 4. So +4, +4 for the first two up to term 3, A3. But then suddenly +24. So it's not +4 for all of them. Doesn't work. If we imagine that it was perhaps a geometric sequence, then we would say, well, the first one times 2 would give us 8, but then times 1.5 would give us 12. That's also, it's not the same, so it doesn't work. This is actually part of a different sequence, but the rules behind it are really complex. And there's this like database where you can throw in a bunch of numbers and it will tell you what the rule is. But this is not a simple type. It's not one of our two key types, so our formulas and such will not work for these. All right, next ones. Find the first 5 terms of each of these. Also, should not take very long, but just take a moment and try this out. Okay, so the first one here, if our first term is 9, then our second term will be 9 times 2. That's the ratio there. So 18, and then 18 times 2, 36, 72, 144. That's it. The other one here in class, we did not really deal with negative R values, but we can still do them. It's not going to be too hard here. So -4 is our first term, and then +8 for our second term, -16 for the next one, +32, and then -64 for the last one. And they would continue on in that pattern. The reason we did not deal with negative R values in class is because our main application is with interest rates, and you don't have a negative interest rate. That's not a thing. Your balance in your account doesn't suddenly just swap between positive and negative. So we didn't really need it, but again, not too difficult to deal with, and we'll have some examples with that here. All right, let's go on. Erase that. So now actually using some of those formulas, or you don't need to use the formula, but it would be helpful here. So find the 9th term of this sequence. And you can write it in the chat when you have it. All right, that was 1 minute. So let's try these out. If we're going to use that formula, first let's just write out what the formula is for the general term of an geometric sequence. What's our formula?
A1 multiplied by
Okay, so AN equals A1
multiplied by R to the exponent of n minus 1.
times the exponent n minus 1. Okay, so I can't write little, subscripts here. That is our general formula for the formula for the general term. And if we look at the sequence here, A1 is just 9. We can see that. We can also see what our common ratio is. What is that?
2.
2, just multiplying by 2 each time. Okay, so we have all, and we know our n, it's going to be 9. So we have all the parts for the formula. So A9 will be, yes, this font is too large. A9 is equal to 9 and times our R value, so 2 to our exponents, n minus 1, which is 9 minus 1, so 8. And we just want to figure that out. 2 to the exponent 8, what is that?
256.
256, and then we just figure out what that is. Times 10 would be 2,560, and just subtract 256 from that. Answer is 2,304. All right. Well, typing this out, it's working out okay so far. We'll see about the later questions. So there's a formula, just put the parts in the formula and figure out the answer. Next ones we'll deal with the partial sum, sorry, 1 second. Gotta fix that animation. Which one is this? Fade out, not fade in. Okay. That's better. So partial sum for each of these, we have the thing on the left and the thing on the right. Thing on the left has a negative R value. So again, will be a little different from what we saw in class, but not terrible, still manageable. So try to find both of these, please. That's been a bit of time. We got some answers coming in. Both of these deal with some pretty big numbers. So as I mentioned in class, like on a test, I might not ask you to like take the final exponent or whatever and evaluate that. So in the solutions I have, we'll just go to the point of simplifying these giant exponents as much as possible and then just kind of leave them there. But lots of answers coming in, I see in the chat. Let's take the one on the left here first. So what is our A1 value? We can see pretty quick, pretty easily. It is going to be -6. And what is our R value?
-2.
Is -2. All right, so those are, and we have our N value here. So what is our formula that we are going to have to use, or that we will want to use here? Partial sum formula.
Sn, right? As if 15 equals to like A1 multiplied by 1 minus R exponent to 15.
Okay, which I'll
over-
just write as 1, or sorry, as N here. And
Minus
before
1.
the
Well,
over,
no,
there's
no.
something else we're missing.
In the parentheses, there should be 1 minus R exponent to 15.
No.
Okay, so here are this -1. Is this part of the exponent or is this outside of the exponent?
Outside.
Okay, this is outside the exponent. So let's write like this just for clarity. So R to the exponent N, then -1. And that whole thing over.
Divided by.
Yep.
R minus 1.
R
Maybe, or
-1.
1 minus R. Oh, yes.
Mm,
R minus.
R -1 or 1 minus R?
R minus 1 because like module of R is greater than 1.
Okay, so our absolute value of R is greater than 1. So this version where it's R to the exponent N -1 over R -1, that's the slightly more convenient version of this. We can't mix and match though. If we have R to the exponent N -1 on the top, then we must have R -1 on the bottom. We can't just like switch half of them. That changes the math. Okay, so we have all the parts and we just put them into our formula here, which let's try it. So I have that here. So just everything substituted in, looks a little nicer than me trying to type it out using the Zoom typing functions here. All right, so on what can we see? We can simplify the parts. The R to the exponent N part we'll deal with second, but the rest of it we can do some simplifying. What can you see here?
3 multiplied and the other part. I mean, we can just divide -6, -6
Mhm.
to +2.
Okay, so I will reduce, simplify to +2 is what you're saying. Okay, so we have a -3 on the bottom and we have a -6 on the top. So that simplifies to just 2. But then we got the big thing in the brackets to deal with. What is your strategy? How might you try to handle that? We could just go straight to a calculator, but let's say we try to simplify a little bit first.
We may open parentheses.
Okay, so we'll do our expanding. We'll just take our 2 and multiply it by the 2 on the outside, multiply by both things on the inside, which will give us this. And then what? can we just directly combine the +2 on the outside and the -2 on kind of on the inside there with the exponent?
No, we should separate -1 from -2.
Okay, there. So the 2 and the -2 are not the same thing. We can't just they're not the same base, so we can't just combine the exponents. But if we reckon -2 is -1 times +2, then we can combine the bases. So we'll split it up like this, and then 2 times 2 to the exponent 15 will just be 2 to the exponent 16. What about -1 to the exponent 15?
It's -1.
It's just -1. So -1, 2 to the exponent 16 minus 2. And then we can just write it like this. Please be careful here. If we compare these two things, the one on the bottom, so 2 to the exponent 16, then make it negative. So this will definitely be a negative number. So the exponent is coming first and the negative sign is coming after. The other one here, -2 in brackets, then exponent 15, it's -2 that's being multiplied by itself multiple times. So don't get confused about the order there. Okay, and then that number 2 to the exponent 16 is 65,536. That's a negative, then -2. So that's the answer that you guys were giving me in the chat, -65,538. So that's how we get there. I'll just kind of leave it like this. This looks, this is all right for our purposes. I also kind of ran out of space to type it there. All right, on the right sides, some people gave answers for this. So let's see what we could do here. If we first just take all of our parts and substitute them in, then we will need to know what all of those parts are. So let's talk about that first. What is our first term here?
3.
3. So 9 times 1/3, 9/3, that's just 3. And our common ratio?
1/3.
1/3. So we could figure that out by just finding the first and second and third term maybe, and then just seeing what the common ratio is. Or we can recognize that we have some constant and with an exponent that is our index. So that's going to be the common ratio almost every time. There's some weird special cases, but that most of the time that will work. In this case, it definitely works. So we'll just take our parts. We'll put them into our formula. Which version of the partial sum formula seems more convenient here? Do we want the one where we have the r minus 1, or do we want the one where it's 1 minus r?
1 minus r.
1 minus r. The absolute value of r here is less than 1. It's positive, somewhere between 0 and 1. So that's the version we're going to want. And we have that here with this first line. Okay. And if we are going to try to simplify this, so our 1 minus 1/3 in the bottom, just simplify, that's 2/3. And then a few things we could do here. So if we take the number on the bottom, let's get rid of the fraction on the bottom. So multiply everything by 3/2, which will give us this. So 9/2 on the outside, and then on the inside here, also simplified our exponent 1/3 to the exponent 10. All right. If we were, again, trying to simplify this without our calculators, what would you want to do at this stage?
We may expand parentheses again.
Okay, so we'll do our expansion, open up the parentheses. So 9/2 times 1 minus, and then just 9/2 times our 1/3 to the exponent 10. So 9 on the top, 2 times 3 to the exponent 10 on the bottom. And one final step to simplify.
We can cancel out the second fraction by 9.
By 9. So we'll have, tell me what the new version of the fraction will be.
Like 1/2 multiplied by 3 exponent to 8.
8s. There we go. So we'll have 3 squared on the top, 3 to the exponent 10 on the bottom. So we just subtract 2 from the exponent on the bottom. And there is our number. So our exponent is fairly large here. So this is not an infinite sum question, but we could even see what the infinite sum would probably be here. The two fractions that we have, the one on the left, 9/2, that's 4.5. And the one on the right, what is that going to be? What approximately?
It's going to be close to 0.
All right,
Because-
very, very close to 0. That's a 1 over some really big number will be almost 0. And as our index increases, as we have a larger sum, it will get closer and closer to 0. So it'll be 4.5 minus like a vanishingly small number, which will turn out to be almost basically 4.5. If we did an infinite sum here, that's what we would get. Okay, so I saw some people write in the chat some very large numbers here. So I think we might have had some confusion with the exponents here. So the 1/3 to the exponent 10. So just 1/3 to the exponent 10 is the number that we should be getting. I think the other numbers that people had were probably doing 3 to the exponent 10 instead of 1 over that. I'm not sure. Okay, so I'm not writing this by hand, so it's a little hard for me to judge how much time it's taking you guys to write this by hand or copy this out or whatever. But I think we are ready to go to the next questions.
Yes.
Yeah, okay. So far, just pretty straightforward, taking our formulas, putting the things in the formula. The rest has just been some algebra, rearranging, maybe some stuff there, but the use of the formulas was pretty straightforward. All right, 2 questions about infinite series, and then we will get to the harder question that I've prepared. So these 2 should be even quicker than the previous ones that we had. Please take a moment, tell me what each of these are, and then we'll talk about them. All right, let's talk about these ones. Our infinite sum formula. Can someone please tell me what that is?
A over 1 minus R.
Oh, okay, so A1 over 1 minus R. That's it. Okay, for the one on the left, what do we have? We have A1, we can see very clearly is just 6. What is our R value?
Negative 1 over 3.
Okay. Negative 1 over 3. All right. So again, it's a negative R value. Sorry, I really wish I had my writing tablet thing. I just want to show you what the sum would be doing here. So let's just try to write this here. Let's do a little exploration here. S1 would be equal to what?
6.
6. So sum of just one term is just the first term. What about S2?
4.
4. What about S3?
14 over 3.
Okay, 14 over 3. And we can keep going like that. I guess it's a little hard to see from these numbers. Again, that's why I really, really wish I had my thing. So the pattern that we would notice if we put this on a graph, we would get like this and then down. The other infinite sums, when our R value is positive, the pattern we get is basically this. So it kind of goes up and then it gets shallower, shallower, and eventually goes almost horizontal like this. With a negative R value, what happens is we would start at 1 point, could be positive or negative, and the next value would go down and then up and then down and then up and then down and then up and then down and then a little closer and closer like this, sort of swapping back and forth, jumping up and down. Eventually it would converge, it would get closer to the same one thing, but it would sort of jump up and down rather than having sort of a smoother kind of line connecting them. So that's the difference with the negative values. If we wrote out more of the numbers, it would become more apparent how that is happening. Anyways, that's just kind of the visual sense of what is happening here. But if we take our two parts, put them into our formula, so 6 over 1 minus negative 1 over 3. So on the bottom, we will get 1 plus 1 over 3, 4 over 3, and invert your fraction and multiply 6 times 3 over 4. So that's 18 over 4, 9 over 2, 4.5, which is what everyone gave me in the chat. Okay, so let's do this for the other one. For the one on the right, what is our A value, A1 value? All right, sorry, I'll just write it. It's 6, it's pretty clear. What is our common ratio?
2.
2. So if we take these parts and throw them into our formula, S infinity is equal to 6 divided by, which version of the formula are we going to use here?
R minus 1.
R minus 1, you say. Okay, so that would be R2 minus 1. And then that's 6 over 1. So is equal to 6. Let's see what happened with the other version of the formula, because we did say that those two formulas for partial sum, at least, if we switch the order, or we just multiply the top and the bottom by -1, it doesn't matter. We'll get the same answer. So let's try that out here. Let's copy this and text and copy this. So let's try this with 1 minus r, 1 minus 2. And so then on the bottom, we would get 6 over -1. So what would the infinite sum be?
-6, but it doesn't make sense.
You're right. It doesn't make sense. What went wrong here? Every one of you fell for my trick. I saw, and everyone has the wrong answer in the comments. What did you not notice, and what are you noticing now that I'm pointing it out?
It's supposed to be infinity, right?
Yes, this is infinity. Why is it infinity?
Because the numbers will keep getting larger and larger.
Look, that's what infinity means, but specifically with our formula, what went wrong when trying to use this formula?
Because r is positive, so it's greater than 1.
Okay, not the positive part, but greater than 1. Absolute, yeah. Absolute value is greater than 1, so this formula doesn't work. We can't use it. It only makes sense when the absolute value of r is less than 1. So infinite sum here is infinity. Also, the answers that you guys were writing in the chat, like 6 and 12 and -6, just add up the first 3 numbers. Like, look at what we would get there. We would get 18, first 2 is 18 plus 24. Like, we're already at 42, and we're just going to keep adding bigger and bigger numbers. It's not going to suddenly drop down to 6. There's no negative there. Just with the numbers that we can see, we can already know that the answers that you guys gave don't make sense. And then a little deeper thinking, yeah, that formula, only when r is less than, or absolute value of r is less than or equal to 1. Okay, so that would have been a really good exam question, but I've done it here, so you guys are wise to the trick. So spoiled. That's all right. I'll do it to the students next semester. Let's go on to the actual kind of harder question that I had prepared for geometric sequences here. This one's going to take a bit of work to figure out. So we'll kind of puzzle through this together. We'll do this one, and then how's our time? This one, we'll do our break, and then we'll come back and work on the interest stuff. So I have this situation. Fourth term of a geometric series is 56, and the sixth term is 7 over 8. And we want to find the infinite sum. And we're going to kind of just cheat here and assume that our R value is positive. What do you think we could do?
When R is, we have to make up an equation.
Okay, tell me an equation. Tell me one of them.
A4 is equal to
A4 is
A1
equal to 56. We have that. Okay, tell me what you were going to say. A1.
Yeah, multiplied by A2 multiplied by A3 is equal to 56.
Okay, and what will we do with that? Wait. A4 is not equal to A1 times A2 times A3. A4 is equal to A1 times the common ratio 1 to 3 times. That's different from saying A1 times A2 times A3. So we have the fourth term is 56. We have the sixth term is 7 over 8. So we have to do something with these and make some kind of equation.
Just make two equations for A1.
Okay, tell me what the equations would be.
So the first one would be A1 equals to 56 over R exponent 4. Second one is 7 over 8 R exponent 6. And then you just equal both of them together and then find R.
Okay. Yes, that will work. That is not the thing I was imagining, or the thing I have typed out here on the bottom. So let's just write that out. So actually, it's saying it a different way, but I think it is the same as what I have typed out on the bottom here. So I'm gonna write this in a slightly different way, kind of using our general term formula a little more directly. So for A4, we know that A4 is 56, and let's use our general term formula. So 56 is equal to A1 times R to what exponent?
4. Oh, I'm sorry, 3.
3, there we go. So 4 minus 1. So A1 times R to the exponent 3 will give us 56. So that's one equation, two unknowns. That is not very useful on its own. But we were also told what A6 is equal to. A6 is 7 over 8. So we can build something here too. So A6, 7 over 8 is equal to A1 times R to what exponent?
5.
5. Okay. Now, does that look like something we can maybe use? Two equations, two unknowns.
No, but you can rearrange and then substitute.
Okay, well, so like we can do something with this. This is a system of equations, two unknowns, so solvable. We can work with this. When we did this, like way back when we did elimination in week 3, and also in the we had a question like this in the previous workshop. We did this two equations, two unknowns for an arithmetic sequence. We did our elimination. So we had things like what you see down here in the bottom left corner. We took one equation minus the other equation, and the A1 terms canceled out. And then we were able to solve for the D term. If we try to subtract these two, is that going to be useful? Will that help us?
No.
No. What could we do instead?
Well, what I did is just find A1 for both equations.
Okay, so you rearranged them to solve for A1 and then you substituted those equal to each other.
Yes.
Okay. What we'll do with it'll get us to the same thing with just like a slightly different method. But I want to, so substitution would work, and it's good that you recognize that. What about elimination? I'm going to tell you that elimination is still possible. We can't subtract, but we can still follow our elimination method. What's the other way we could maybe eliminate?
Divide them.
Divide them. So just like we talked about before, where, you know, the two sides are equal. If I take, like, say the first one, 56 equals A1 times R cubed. if I divide both sides by 56 or divide both sides by 5 or something, dividing by the same thing on both sides, so it stays balanced, so it's fine. And this 7/8 equals a1 times r to the exponent 5. It's the same. Like, we don't know what a1 and r are, but we know that the two sides are equal, so it's balanced. So we're just taking the two equations and dividing. So divide the left side by the other left side and the right side by the other right side. This is still like a valid mathematical thing that we can do. So if we do this and just simplify and such, then we will get 56 times 8/7. The a1s disappear, r to the exponent -2. 56 and 7. So 56 is 7 times 8, right? And then dividing by 7. So we can just, okay, I didn't have time to put in all the animations here. So this line, the 7s disappear. We have 8 squared, and then we have a negative exponent. So just flip both things and then take the square root of each side, and we get 1/8. This is why I was saying assume r is positive. Otherwise, we could have 2 possible values for r here. Okay, so we figured out r. Now what can we do to figure out a1?
Substitute.
Substitute. So we can substitute into either of our 2 original equations, the a4 one or the a6 one. I chose to do a4. Yes, so 56 is equal to a1 and r cubed, 1/8 cubed. And so let's just do a little bit of algebra here. So 1/8 cubed. Bring that over to the left side and we'll get this again, 56, 7 times 8. Let's just separate out the 8. 7 times 8 to the exponent 4. And I'm going to say the question is not asking us to figure out what a1 is. It's only asking us to find the partial sum. So I'm going to say, we don't care. Let's just leave it like this. We don't need to write out what's the exact number here. It's probably going to kind of get canceled out or simplified somehow anyways. So let's just leave it like this. If we're not told give a1, then we don't need to actually pull out the exact number there. So let's just leave it like this for now. Okay, are we ready to use our infinite sum formula?
Yes.
Yes, we have r, we have a1, so we just throw everything into the equation. Here is a1 over 1 minus 1/8. Remember, there is no infinite sum formula where it's r minus 1. It's only ever 1 minus r because our r value must be less than 1. Our absolute value must be less than 1. So that's, and then we're going to get a 7/8 on the bottom. And then we just invert and multiply here. There's the top, there's the bottom, now inverted. And the 7s are canceling out. Fantastic. I didn't want to deal with those anyways. And we have 8 to the exponent 5 here, which I guess I should have written another step or two. 8 to the exponent 5. Let's rewrite this as a power of 2. 2 to what exponent?
15.
15.
15. Okay. And then whatever that is, we can put that in there. All right. So our infinite sum here is 2 to the exponent 15. And we didn't need calculators or anything. just some clever algebra. So the thing I want you to notice with this question is we can take two equations and we can divide one equation by another equation. It's not just adding or subtracting. The division or multiplication is also a valid process. Not usually useful. Normally we wouldn't do this, but in this case, it definitely works. So this is a nice longer but good general pattern that will work for any case for a geometric sequence. Give me any two terms and we can do this process and we'll figure out exactly what our R and A and everything is. There's a shorter method that we could have done here. Does anyone see what that might have been?
I guess we had to divide A6 to A4.
Yeah, A6 divided by A4 would equal to what?
1 over
R
8.
exponent to no R exponent to exponent to R squared.
R squared. So A6 over A5, any term divided by the previous term is R. So dividing by two previous terms should give us R squared, because A4 times R again. A4 times R squared gives us A6. So therefore A6 divided by A4 should give us R squared. And we know what A6 and A4 are. We could have just done that pretty quickly here and we would have gotten that R is equal to 1 over 8. So that would have been a little shorter, faster. But if these two terms were really far apart, that'd be kind of awkward. And it's nice to kind of notice or be aware of this dividing by fractions. Oh, sorry. Division elimination, division version of elimination that works in a nice general case here. All right, that was the harder question that I had prepared for us here. Anyone have questions about this one? No, we're good. Okay. So it is my clock here. 8:33. We're halfway through. So let's take a 10-minute break now. We'll come back and talk about interest stuff, and hopefully that will be okay with just this typing thing. So come back at 8:43, everyone. See you in 10 minutes. Okay, let's let's resume here. I almost finished the last one, typing it out. We'll see how it goes. So second part's talking about interest, so applications of these concepts of infinite arithmetic sequences and geometric sequences just applied to finance. So we talked about in class either yesterday or today, depending on your section, how, or kind of an exploration of how simple interest is really a type of arithmetic sequence and how compound interest is really a type of geometric sequence. So I'm not going to go through all of that. I'll hope that's, sorry, 1 second. Let me hide those formulas because we should remember what they are. I'll show them if we need them. But I want you guys to tell me what they are. Okay, there we go. All right, we have this situation. So take a moment and try to calculate what each of these two things are here. What is the, and feel free to use a calculator here. These questions are a bit hard to do without one. So under simple interest and under compound interest, these scenarios. Go ahead. Okay. Sorry, that was more time than what I should have given you. I was still trying to prepare the thing on the later question. Okay, simple interest, compound interest formula. Can someone, or let's tell me, what is our simple interest formula first?
It's E equals, right? This
Mhm.
one equals P, yeah, this principal multiplied by, in the parentheses, 1 plus little case I multiplied by T.
Okay, good. So P is principal. Explain what principal is in simple terms.
It's original amount of money that is put in the beginning,
Right.
starting money.
So it's our starting value of the loan, of the investment, of the whatever. What does AT represent?
Final value.
Final value, value after T years, after 5 years, after 10 years, whatever. So the lowercase I represents what?
Interest
Interest
rate.
rate.
Right, interest rate, not the dollar value, but the rate at which interest increases, and then T is our time in years. So our first one here, pretty straightforward. We just have all the parts, throw them into the formula and see what we get. AT, I can write this a little larger, got space. AT is equal to 33,500 pounds here times 1 plus 0.11, so 11% as a decimal, and that times T, which is 5. So 1 plus 0.55 and 1.55. And then we go reach for our calculator to figure out what this is. And someone tell me this, or sorry, you guys have this number in the chat. I have a few, no, okay. For A, everyone has the same number. 5,425. Is there a decimal to that, or is it exactly that value?
Exactly.
Exactly.
Exactly. Okay. Works out cleanly. All right. So there is our simple interest. Again, with this formula, it's not too hard to work with. I could give you any of the other 3 parts and just calculate what the final one is. Let's go over to our compound interest situation. What is our compound interest formula, compounded annually?
P multiplied in parentheses 1 plus I to the exponent of T.
Tell me where the T exponent is exactly.
After the brackets.
Okay, so it's outside of our brackets, outside of our parentheses. So pretty similar, but T is in the exponent and it is outside. So we will again just put all the parts into our formula. A T is equal to, I'm going to be lazy here and just copy what I wrote on the other side and just change some parts. This to the exponent 5. And so this will be 1.11 to the exponent 5. And once again, calculator will probably need to figure this out. You guys told me in the chat 5,897.7. Okay, I see. Vincent, you're telling me each year.
Yeah, because I thought it's calculated annually, right? So yeah, I try to find each of the values each year.
Yeah, so okay, what I meant by yeah, each, so sort of compounding interest is sort of what I meant with that. Didn't mean that you had to find it for every single year, but that's fine. You still got the right answer at the end. So there we go. Just put the things into the formula. I do have some slightly harder versions of this. Next. Yes. This one here. So the phrasing's a little weird. So read the sentence carefully to know exactly what it is asking you to provide.
Can you back to the first question, please? For 1 second only.
This one?
Yes.
Yep.
Thank you so much.
There's a screenshot button on your computer. It comes with one built in. I think it's really funny that you guys use your phone to like take a photo of the screen. Anyways, okay, go ahead. Try to calculate our number here.
I might be wrong in this one because I don't know what it's asking.
Okay.
It's a bit confusing, the
Yes.
language.
Yes, I agree. I think it could definitely be written more cleanly, but I've seen a lot of books and stuff that write it in this way, so that's why I wanted to expose you guys to this style. All right, let's look at our answer here. So interest is compounded. So we have our compound interest formula. What's the information that we have been given here? Tell me the easy parts first.
80 is given.
Okay, so is it AT or is it P? That sounds like the harder part. Tell me the easy parts first.
80.
Again, that sounds like one of the harder parts. The other things that we've been given.
Sorry, I is given.
Okay, so I is pretty straightforward. So 4.5%, so 0.045. What else do we have?
T is given 5.
Okay, T is given as 5, and this is compound interest. All right, present value of this due in 5 years. So the 10,000 pounds, is that the principal or is that the value after 5 years?
£10,000 due. So you have to pay 10,000, right?
Okay,
5
so
years.
does that mean it's the principal or the final value?
Principal, maybe.
Yeah, 10,000 once at the
Final.
beginning.
Okay,
Professor, 10,000 is a final.
All right. Some people saying the starting value, some people are saying is the final value. So two things we can notice here. Calculate the present value. That's part, and then sort of do in 5 years, 5 years from now. So calculate the present value of something that would like change this way in 5 years. This part is saying do. So this would mean like I loan you money, and then after 5 years, it's going to be worth £10,000, and then you owe that back to me. I am due £10,000. So this confusing phrasing, but this is talking about the final value. And we here with present value are being asked to find P. So those are what the parts of what the question is trying to ask us here. All right, so given that, we can go to our formula. AT is equal to 10,000, and so 10,000 is equal to P, which we don't know, and 1 plus, I'm just gonna skip here, 1.045 to our exponents 5. So then 10,000 divided by 1.045 to the exponent 5 is equal to P. And we just calculate what P is. So P will be something less than 10,000. This is kind of a smaller interest rate, so it's probably not going to be huge, or sorry, a huge difference, but still be a bit less than 10,000. I'm seeing, okay. What are all the versions you guys have in the chat? That was a B. Sorry, that was looking at the wrong part here. Okay, so 8,024.5 something. So that looks to be about the right amount here. The 9,903, that's not small enough. The growth rate would be large, and Mirbos has a number sort of calculated in the other direction if this were growing, I think is what he's calculated. If we were trying to start with if 10,000 was the current value and we're trying to calculate value after 5 years. Okay, so again, just punch the things into your calculator and figure out the numbers here. I think I might have forgotten to much of this in one of the sections. I could choose numbers that would work out kind of, very conveniently, and we don't need a calculator, but they would be extremely unnatural, like really bizarre interest rates that never happen. So for the sake of showing you some numbers that are a bit more realistic, we've had to, again, cheat and use our calculators here. All right, I'll give you another one that's going to be a bit more, well, you'll see. So read the question carefully here. And the math part isn't going to be that hard, but there's a little trick you're going to have to recognize at the beginning here. So give this a shot. All right. So this one here is a little, there's a little trick at the beginning, and then the actual math stuff that's happening a bit later is also going to be not super challenging, but a bit more than what we've seen so far in class. So this is compound interest formula. Okay, there we go. What have we been given in this question?
T.
T.
T. Okay, so for A, T is equal to 12. Equal to 12. What else have we been given?
It should be like principal should be doublet.
Okay, tell me. Well, let's talk about the other parts first, and then we'll get to that. Again, that's going to be kind of the harder part here. So there are the T values. What else have we been given? Or actually, sorry, that is, no, you're right. So our I value is question mark. We don't know. We have also AT in our formula and P in our formula. So right now it looks like we have three things we don't know. So what can we do?
Just make up any principal value and then multiply that principal value by 2 to get the T.
Okay, that would work. I'm going to say we can keep things a little more general. Can we say that AT, our final value, is equal to something?
2P.
2 multiplied by P.
2P. So whatever P is, just double it. We don't have to actually make up a value. We'll just leave it as the variable. Whatever it ends up being, it'll just AT will be double that thing. Okay. So if we put that in our formula here, then 2P is equal to P times 1 plus IT. And I'll leave T for now because we have a few different variable values of it. Then if we simplify this, P just disappears. So we don't need to know P and we don't need to know the final value. All we need to know is the ratio between the two, doubling. So 2 is equal to 1 plus I to the exponent T. All right, so let me just make sure I have my animations correct here. Yep. So for A, we are given this situation here. All right, so what is our next line? Using our exponent rules, what do we have?
Move the exponent to the left. And
Okay, so what will the left side be?
2 exponent 1 over 12 or just root 12 of 2.
Okay, and that's equal to 1 plus I. And if we simplify that, then 12th root of 2 minus 1 equals I. And that thing we just throw in our calculator. 12th root of 2 is not going to be very easy to figure out by hand. It'd take quite a long time. So we could pull out that number. Again, let's just leave it here. There's a button on your calculator to do that, but we want to figure out just kind of the math part of this here. The algebra part of this rather. The other two, it's going to be the exact same thing, except that we have a different exponent and it's going to be a different root. Let's just make sure we understand what the pattern will be here. So of these three values, which one will be the largest? Which one will be the smallest?
The third one would be the largest.
Third one will be the largest, okay? And which one will be the smallest?
The first one.
First one. Okay. So looking at the math, we can see that. So some number times itself 12 times will equal 2. And then on the one on the far right, some number times itself only 5 times will equal 2. The one that's times itself 12 times must be a smaller number. If 12 of them will equal 2, but on the other one it's just 5. Also, intuitively, we can just think about the problem. If we have 2 kinds of investments, and in one of them, it takes 12 years for our money to double, and in the other one, it takes only 5 years for our money to double, which one's giving us more interest? It's the one where it takes only 5 years to double. So that would be the nicer option if we get it. So higher interest rate with option C, moderate interest rate with option B, and then a lower, probably safer interest rate with option A. That always happens. If you want greater return rates, you are assuming more risk in your investments. Okay, so the trick here is just noticing AT is equal to 2P, and then we don't actually need to know either of them. They'll just disappear. The P variable will disappear, and we'll just have 2 equals whatever, and then solve from there. We could do the same thing and say, how much time would it take our investment to triple in value or become 10 times bigger or whatever? All right, the last one. I am almost finished preparing the slide. I've been busy working at this the whole time while you guys have been solving. It's going to be a little harder. You may or may not know the math tool that we need. If you don't, that's all right. So take what we have here and just simplify as much as you can, and then you'll get a spot. You'll hit a spot where you say, I have no idea what to do here. And by that time, I should be ready to show you. So take a moment and read this and see how much you can figure out.
Oh, it's log, isn't it?
Yes, logarithms. All right, I think finally got it ready. There we go. All right, ready. So, oh, a little bit in the corner. I need to erase. There. Okay. So same situation is just double. So the part that we have on the left here, same rule, same principle holds. Don't have to do anything special there. And then if we put in those values, now we don't have a t value, but we have an I value. So 0.06, and just add those two numbers, we get this. Okay. So now we need to solve for an exponent. So note what we did on the other one here. We had an exponent that we wanted to move and we didn't know what the base number was. So that's a thing that we can do with our roots, cube roots, square roots, all those. But here, the exponent is the mystery thing. Sorry, gotta this one, 1, 2, 3, 4 animations. I don't know if these are going to move properly. Damn it. Sorry. Normally, this all works fine, but again, my not having this writing tablet makes things a lot more annoying.
Why are you using Google Slides?
Because they're all online. I can use them from anywhere. I don't like relying on especially in the classrooms, like I don't want to be plugging in like my USB drives or whatever into random classroom computers that could be loaded with viruses or whatever. I find this to be much better, much more reliable. I don't do fancy animations usually, which is why Google Slides is normally not a problem for me. But yeah, you're right. This right here, building these animations, moving these around, PowerPoint does a much better job with these. Let's double check. 1, 2, 3. Dun, 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 dun. There we go. Okay. All right. So how do we get t? How do we figure out that thing here? So let's just do a little math exploration here, and yet another one of these. 2 cubed is equal to what?
8.
8. Easy. If I give you this, 2 to something is 2 to something, or 8 to the something root gives us 2.
Cube
Three.
root.
3. So cube root of 3. What if we have this though? What if we have a mystery exponent? I should have written that one a little differently. Mystery exponent here. So it turns out we have this thing with like multiplying the opposite is dividing, with adding the opposite is subtracting. But exponents are a little weirder. We have 3 different types of things, a base, an exponent, and a power. So we actually need 3 different operations to be able to kind of like complete the circle there. So exponents, 2 to the exponent 3 will give us 8. A root, so cube root of 8 gives us 2. And then we have this other option called logarithms to figure out what's the exponent. So this thing here is basically saying 2 to what exponent gives us 8. So this thing here is this yes, like this here. So log base 2 of 8 then is equal to 3. So 2 to what exponent gives us 8? Well, it's 3. How do we actually evaluate a log? So that's kind of that's what answer it gives us. How do we actually pull out a number? Turns out it's a whole bunch of difficult calculus stuff. We are not going to go into how that happens. You can just know that on any calculator that you have, even old, simple, boring, dumb calculators, they will have an option. You can kind of, it's out of focus, but right there it says log on this very simple phone calculator. There's a button that'll work for that. The more general case would be this, if we want to show it like this. A to the exponent equals C, then therefore A is equal to the B root of C, and log base A of C equals B. That's the complete circle. Probably some of you didn't get that far in high school with the logarithms part, but those 3 operations are all kind of complementary and work with each other. So if we come back to our problem here, we can figure out what T is by writing it this way. So log base 1.06 of 2 equals T. Okay, so 1.06 to what exponent gives us 2? Well, with the 2 cubed equals 8, it's pretty easy to intuitively see it, but like, I don't know, 1.06, like I don't have those memorized. You probably don't either. So there's the way that we would figure this out. Logarithm rules, which I'm not really going to go into. I'll just kind of show you this one. Says that if you have one thing with some bases and whatever that you don't like and are hard to work with, you can rearrange them to be like this. You can make a new base, log base, so 10 on each of these, and then turn it into a fraction. So log base 10 of 2 over log base 10 of 1.06 is the same as the previous thing. And the log button on your calculator, we care about this one, base 10, because the log button on your calculator is base 10. If it doesn't say what the base is, it's base 10. So what we can do now is on the calculator, type 2, hit the log button, and big long number. There you go. That's that number. And we can do the same thing here. Log, type in 1.06, hit the log button, other big number, divide the 2, and there's T. Again, we can type it into the calculator and figure it out there. Did anyone give us that number? Vincent gave us 11.9 for the first one. 11.9. Okay. And for the other one here in the middle, with 3%, it's the exact same thing, except the numbers, it's all 1.03, 1.03, 1.03, and then we'll get a different T value, which we also have, thank you, 23.4 would be the T value here. So using this logarithm tool, we can see that if we want our investment to double, and the option that we have is like, here's a savings thing, a bond or whatever, that's guaranteed 6% compounded annually, then we'd have to leave our money there for 12 years in order for it to double. Or if it's an even lower rate, like 3%, which is a pretty terrible return rate for your investments, it would take 23 years in order to just double in value. That's really not that good. You'd want to find something better. At least like 8% would be nice. Like 6 to 8% is sort of a good, safe amount. Okay, so if we had a bit more time, I would have sort of shown you like typing in the numbers for the logarithms a bit more slowly and such, but it took forever for me to type all of this out and build all these animations, or like 15 animations on just one slide like this. So I didn't have the time. I am also annoyed that I am heavily reliant on that one writing tablet thing. And if I don't have it, it creates all this extra work. So I don't know. I guess I'll have to buy a second one or a spare or something. All right. On our tests, on our exams and stuff, there's no way you're going to calculate these logs on your own. I haven't even shown you how to do it. So this won't be on an exam because this is a calculator only question. Figuring out roots like on the previous question here. This could be possible if I gave you very artificial numbers that just kind of work out nicely, but it's extremely unrealistic. So I'm not going to give you those situations as well. But it's good to know. Little bit of extra math skill here. We can solve for an interest rate if we need to, and we can solve for a time as well if we need to with our fancy logarithm tool. Okay, that is as far as I wanted to go today. Does anyone have questions about these two examples? If logarithms are weird for you, just remember this thing on the far right. That's the core idea. If you spend enough time staring at that, it will start to make sense. Any questions people want to ask?
I have an unrelated question.
I think I can guess what it is. Let's formally finish here, and then you can ask me your question. So we're a bit over 9:30. Thank you for listening, everyone. I'll put the recording of this up online a bit later. The harder question with like the two random terms in the geometric sequence, and then figure out the rest of the sequence. It's possible to do that without the elimination and dividing the two equations. So I can just kind of recognizing, oh, it'd just be r squared if it's two terms away. So I think that kind of thing would be a fair question on an exam, but these last two with the interest rates, calculating interest rate and calculating time for a compound situation would be a bit unfair, but so wouldn't be included, but just nice to see. All right, I'll see all you guys on Monday or Tuesday next week. Enjoy your evening and your weekend.